Hello, good morning to all of you. I hope all of you are doing well. So in today's class, we'll be starting with the basic of 8085 programming. So to start with, whenever we write a program using any of the programming platform or any of the programming language, what we do is we make use of programming variables. Now these variables are used in order to hold value during execution. Categorically stating, there are three different types of variables. The variables are named as simple variable, composite variable, and pseudo variable. A simple variable is a variable that holds only one value at a particular point in time, whereas a composite variable is a variable that is capable of holding more than one value at a particular point in time. Likewise, pseudo variable is a variable that is not actually a variable but it's capable of behaving as a variable, and these are CPU registers which are capable of holding values during execution. So example of simple variable would be a simple integer variable. Example of composite variable would be an array. An example of pseudo variable would be the CPU registers as I have listed here. Now in 8085 programming, what we do is we make use of such pseudo variables. Now here there are 7 pseudo variables, namely A, B, C, D, E, H and L. Again, I repeat it. Here, there are 7 pseudo variables, namely A, B, C, D, E, H, and L. Individually, these pseudo variables or registers, are of 8-bit size and it's capable of holding 8-bit data. As and when required, these 8-bit registers can be combined to form 16-bit register to hold 16-bit data. So the register pair are as BC, DE, HL. Now BC, DE, HL are the three register pairs that can be used for handling 16-bit data. Now one of the most important thing that you need to note here is in any of the operation that you perform, A will be considered as one of the default operand. Again, I repeat it. If in any of the operation that you perform, A will be considered as one of the default operand, and it's called as the accumulator. Now to begin with, let us take a very simple example where we try to add two hexadecimal number. Now the two hexadecimal numbers are stored in register A and B. So A and B holds the value that are to be added. Now A holds 06 and B holds 05 H. Now here H basically refers to hexadecimal number. Now here we have also provided the location where the result is to be stored. So the result is to be stored in F000H, and the program has to start from C000H. So please don't get confused. Here the values that are to be added are stored in registers A and B. The location where the result is to be stored in F000H, and the starting location is C000H. Now all of these are hexadecimal in nature. So hexadecimal is base 16 number, right? So anything that has a H succeeding it, it's a representation for hexadecimal. So here what I've done is I've built a very simple concept like in C. So you have A being initialized to 06H, B being initialized to 05H. So here, as I've already said, A will be one of the default operand whenever any of the operation is performed, and it's called as accumulator. So what I'll do is I'll add the content of A and B and store it in A. So I'll add the content of A and B and I'll store it in A. So that's why I've used a representation of shorthand operator. So A plus equals to B. Now finally what I'm doing is I'm moving the content of A to F000H. So again what I'll do is I'll repeat it. So I've initialized A to 06H. I've initialized B to 05H. And then I've added the content of B to A and stored the result in A, and then I move the content of A to F000H. Now, if I have to represent it using 8085 instruction set, so A equals to 06H will be replaced by MVI A, 06H. Now what does it basically imply is it implies that I am moving a hexadecimal value 062A. So it will be interpreted from right to left. So I'm moving hexadecimal number 062A. Now why it is called as MVI is it stands for move immediate data. Now move immediate data, here it implies, just see in the third notion here, I'll tell you why it's called as MVI, because just see 3E is a representation for MVIA. I'll come to that. Please don't worry about it. 3E is representation for MVIA. Now likewise 06 is the value. So now 06 is immediately stored after the executable code for A. I'll again repeat it. 06 is immediately placed after executable code for MVIA. So 3E is a representation or an executable code for MVIA. So as 06 is immediately placed after the executable code for MVIA, so that's why it's called as move immediate data. So move immediate data 06 that is placed after the executable code for MVIA. So that's the reason why it's called move immediate. So what will happen is 06 will be moved into register A. Now likewise 05 will be moved into register B. So here it is same as that of copy. So 06 will be copied to A and 05 will be copied to B. So once 06 is copied to A and once 05 is copied to B, then what we can do is we can add the content of B to A. So here just see the instruction is only written as add B. So add B implies you are adding the content of A and B and storing the result in A. Again, I'll repeat it. Here, add B basically represents that you are adding the content of B to A and storing the result in A, because as I said, A is one of the default operand. Then what I need to do is I need to store the content of A to address location F000H. So STA, it stands for store the content of accumulator in the address specified. Again, I'll repeat it. STA stands for store the content of accumulator in the address specified. So here the address specified is F000H. So what will happen is it will store the content of the accumulator in F000H. Now once the content of accumulator is stored in F000H, then what we can do is we can stop. So in case of C program, what we write is we write closing braces to represent the termination of the program. Likewise, here what we have is we have halt instruction HLT. So whenever HLT or a machine code or executable code for HLT is encountered, the program terminates. Right. Okay. So here, what I've done is I have created a representation of adding A and B and storing the result in F000H using the instruction set defined for 8085 programming. So MVI A, 06H basically means move immediate data, that is after the opcode for A or executable code for A to A. Right. Again, move immediate data 05 to the register B, then add the content of B to A and store the result in A, then store the result of accumulator in F000H, and finally the program terminates, right? So now you may be wondering what is 3E, what is 06, what is 06 again, so and so forth. Now MVIA is an instruction that has some representation in terms of execution, because you see what we cannot do is we cannot place MVIA to the microprocessor. We need to create a representation of the program in binary form. So each of this notable instruction that you have, MVIA, MVIB, MVI add B, STA, HLT, these are given unique code of execution. Now these are called as operation code. So each and every instruction is given a unique code for execution. This is called as an operation code or opcode. So there are 256 possible instruction with 256 possible opcode. Now Again, what I want you to do is I want you to draw your attention to this particular table. Now, just see here, this is the instruction table for 8085 microprocessor. Now, if you see here, what we have is we have the instruction set. We have the instruction set and the corresponding hex code or the operation code or the executable code. Now, just see here, if I go to add B is 80. Again, I'll repeat it. Add B is represented by your opcode 80. Add C is represented by opcode 81. Add D is represented by opcode 82. Right? So likewise, each and every instruction that's defined for 8085 microprocessor has a set of operation code or hex code associated with it. So these hex codes are placed instead of the instruction whenever the execution is to be done. So again, I'll repeat it. The hex codes are placed instead of the instruction whenever the execution is to be done. Now, likewise, 3E is the opcode for MVI-A. Likewise, 06 is the opcode for MVI-B. Likewise, 80 is the opcode for add B. Likewise, 32 is the opcode for STA. 76 is the opcode for HLT. So here we'll not call it as 80, 32 or 36 because these are not decimal numbers, these are hexadecimal numbers. So now here, first what we have is we have opcode for MVIA, then we have data 06. We have opcode for MVIB, then we have data 05. We have opcode for add B, we have opcode for STA, then we have the address byte 00F0 and the opcode for HLT. Now, you must be wondering that how would a microprocessor differentiate between whether it's an instruction byte or a data byte? Because you see, everything looks alike because everything has hexadecimal representation. So how does a microprocessor differentiate between a data byte and instruction byte is that always the first byte of the program will be instruction byte. Okay. Again, I repeat it. The first byte of the program will be always an instruction byte. So microprocessor interprets the first byte of the program as instruction byte every time. Now, if this 3E becomes instruction byte, then MVI-A takes in a data byte. So MVI takes in 1 byte of data. So 3E, it assumes it to be instruction byte for MVIA, so it assumes that 06 is the associated data with MVIA. So once the associated data with MVIA is interpreted, then again the next byte will be considered as instruction byte. So 06 is the instruction byte for MVIB. Again, it assumes that the next byte is the data byte for MVIB. Okay. Now, once it assumes that 05 is the data byte for MVIB, then it assumes 80 to be instruction byte. So that pertains to add B. Now again, once it is interpreted as instruction byte for add B, then again it assumes 32 to be instruction byte for STA. Likewise, STA expects 2 data bytes, that is address. So it assumes this to be 2 data bytes for STA. Likewise, once it is exhausted, then the next byte again will be considered as instruction byte. So here, this implies that in case of 8085 programming, there can be different types of instruction based on the number of bytes. So here, MVI-A, as it requires 2 bytes, so it's called as 2 byte instruction. Okay, add B requires 1 byte, it's called as 1 byte instruction. STA F000H, so it requires 3 byte, it's called as 3 byte instruction. So in 8085 programming, what you have is you have a 1 byte instruction, you have a 2 byte instruction, or you have a 3 byte instruction. Based on the requirement, you can use any of these type of instructions. So now, once the instruction, the program that was written using 8085 instruction set has been translated using the equivalent executable code or the operation code, now what we have is we have a representation of the program like this. So 3E060605 8032. I have written 00F0. I'll come to that why I've written so. and 76, right? Now let us further try to understand one important concept that you need to know whenever you're writing a program. Now let us consider that when you are declaring a simple variable a, let us consider that you are declaring a simple variable a is declared as an integer variable and is assigned with the value 5. Now whenever a variable is declared, the first thing that happens is memory allocation is done. So here 2 bytes are allocated to the variable a. So say let us consider that the address locations that are allocated to a are 2000 and 2001. Okay, so here what I've done is I've declared a very simple variable a, and I've initialized a to 5. So whenever initialization will be done, whenever declaration will be done, memory allocation is done, and whenever initialization is done, the value is placed in the allocated memory space. Now a in 16 bits would be like this. So this is the binary pattern for a in 16 bits. We have 8 zeros, then we have 4 zeros and 0101. So the 101 is 5. So this is the representation for 5 in 16 bits. Now this representation of 5 is to be stored in 20, 2000 and 2001. Again I'll repeat it. Here what I've done is I've declared a simple variable a and I've initialized it to 5. So since the type of a is integer, so here 2 bytes of memory will be allocated to a. And the said allocation is done in a manner that the address values are 2000 and 2001. Now representation of a in 16 bits would be, if you binarize it, what you'll have is you'll have this particular sequence of values. So this particular sequence of values to be stored in 2000 and 2001. Now here this address location 2000 is called as lower address space, okay, and the address space 2001 is called as higher address space. Again I'll repeat it. The address space 2000 is called as lower address space, and the address space 2001 is called as higher address space. Now likewise, if the variable would have been a floating point variable which has 4 bytes allocated to it, then you'll have the highest address, lowest address space, lower address space, higher address space, and highest address space. Okay, so we'll be having 4 bytes. So here we have only 2 bytes, so we have lower address space and we have higher address space. Now as per the binarized value of 5, we have 2 bytes in it. The higher byte and the lower byte. Okay, so higher byte has all zeros and lower byte has quadruple 10101. Now let me tell you the way how the value is to be stored in the memory so that there won't be any problem during memory access. Now let us consider a situation. We have lower address space and we have higher address space. So if we store higher byte in lower address space and lower byte in higher address space, again I'll repeat it. If I store higher byte in lower address space and if I store lower byte in higher address space, that means in this particular sequence as in the sequence specified, what we'll have is we'll have data accessed in a different manner, because you know that whenever data access takes place always from the higher address space and then it moves on to the lower address space because it follows the concept of stacks. Again I'll repeat it. Whenever data access is done, always the higher byte is accessed first, followed by the lower byte because it follows the concept of stacks. Now if that is true, then 2001 will be accessed first, followed by 2000. So if that happens, then quadruple 0101 will be accessed first, followed by quadruple 0. So this would be order of data access. So it will be quadruple 0101, quadruple 0. So this is not 5. If you convert it into decimal number, this is not 5. This has occurred because of the reason that what you have done is you have stored the higher byte in the lower address space and lower byte in the higher address space. Okay, and whenever data access will be done, data access will be done from higher address space to lower address space. Okay, so this is one of the important problem that one needs to understand, because whenever you're writing a high level program, this particular thing is automatically managed by the computational system. But here, since we are writing low level program, what we need to do is we need to take care of this. So in order to resolve this particular problem, what we need to do is we need to ensure that the data is stored in the manner it's accessed. So first what I'll do is I'll store the higher byte in the higher address space and lower byte in the lower address space. Okay, I'll repeat it. I'll store the higher byte in the higher address space and lower byte in the lower address space. So if it so happens then whenever I'll access the data, 2001 will be accessed first. So the content of 2001 is quadruple zero here, and the content of 2000 is quadruple zero one. So this is here. So now this is equivalent to 5 in decimal. Okay, so if you convert this binary series, what we'll have is we'll have a 5 in decimal. So this is very important for one to understand that whenever you are storing values that are there pertaining to a variable, and if it consists of multiple bytes, then what we need to do is we need to decompose the value in byte sequence and store the higher byte in the higher address space, lower byte in the lower address space. Likewise, if there are 4 bytes, then highest byte in the highest address space, higher byte in the higher address space, lower byte in the lower address space, and lowest byte in the lowest address space. So that is the way how the data has to be stored. So here, if that is true, if that is true, then f triple zero has in it 2 bytes. F triple zero has in it 2 bytes, that is F0 and 00. So now F0 here is the higher byte, 00 here is the lower byte. Okay, so now what we need to store is we need to store the higher byte in the higher address space, that is C007, and lower byte in the lower address space, that is C006. So just see here, the higher byte, that is F0, is stored in higher address space, and the lower byte, that is 00, is stored in lower address space. So that's why it is represented as 00 F0 instead of F000. Okay, so the higher byte, that is F0 of F triple zero, is stored in C0007, and lower byte, that is 00, is stored in C006. Okay, so that is the reason why it's written as 00 and F0, because higher byte has to go to higher address space, lower byte has to go to lower address space. Okay, so this is true in case of all formats of data. So this is one important thing you need to remember. So now what we have done is we have converted the program written in a concept node to a program using 8085 instruction set. Then what we have done is we have converted the program written in using 8085 instruction set into a set of executable code or opcode and data code, right? Okay, data. And then now what we need to do is we need to store the program in computer's memory. Now, the starting address for storing the program is C000. So in C000, what we are storing is we are storing the byte 3E. So we are storing the byte 3E in C000. In C001, we are storing 06. In C002, we are storing 06 again. In C003, we are storing 05. So likewise, in C004, we are storing 80. C005, we are storing 32. C006, we are storing 00, that is the lower byte of the address. In C007, we are storing F0. And in C008, we are storing 76. Now, once you place 76, then what you need to do is you need to ensure that the value is written into the memory. So you just need to press enter. Okay. So now this is the way how you convert a concept into a program using 8085 instruction set and a program using opcode and store the program written using opcode in the computer's memory. Okay. So I hope it is a little bit clear. So we'll move on to the next example, which will, I guess, help you in further simplifying things. Now, whenever you write a program, okay, so whenever you write a program in any label, say for an example, whenever you're writing a program in a using a fourth generation language or a third generation language or a low level language, right? Okay, it so happens that everything has to be converted in forms of zeros and ones to make the computer understand. So now here, how the conversion is actually done is, in case of C programming, what we do is we use the compiler to convert a high-level program into a low-level program. So here, what we need to do is, since we are doing the conversion, so we are playing the role of the compiler. Okay, right? So here, so whenever we are writing a program using 8085 instruction set and translating into a program using the opcode, what we are doing is we are translating into a binary code, right? Now just see how this particular program actually looks like in computer memory. Okay, so in C000, what we are storing is we are storing hexadecimal value 3e. So 3e, these are two hexadecimal digits, right? Okay, each of these hexadecimal digits are composed of 4 bits, because a hexadecimal symbol is composed of 4 bits, a nibble. Okay, so here just see what we have is we have the representation of the program. So 3 is 0011. Okay, 3 is 0011, E is 0001, triple one zero, sorry. So this is 3E. Okay, so 4 bits representing 3 and the next 4 bits representing E. Now likewise 06, 0000 is representation for 0 and 0110 is representation for 6. So this is 06, right? Now again what we have is we have 06, then we have 05, then we have 80, then we have 32, subsequently we have 00, then we have F0, and we have 76. Now just see, what I have done is I have created a binary code for the entire program, right? So this in case of high level program, a high level programming is the role of compiler. But see how easy it is to get the binary code of a program. So this is the program that actually executes. This is the program that actually executes. Okay, so a program that is written in terms of zeros and ones. So this is a very simple explanation for a program that's capable of adding two numbers. Now let us consider another problem, that is to subtract one number from another number. Now subtract one number from another number. Just see here what we have is we have again one hexadecimal number from another hexadecimal number. Now let us consider the values that are participating, or the variables that are participating are A and B. So these are two pseudo variables or CPU registers. Now the result where the result is to be stored in the location F000H, and the starting location of the program is supposed to be C000H, right? Now again what I've done is I've prepared a concept note for the program. So A is equals to 06H, B is equals to 05H. Then we are subtracting. So now just see, as A is one of the default operand, subtraction will be done in a manner that B will be subtracted from A. Again I'll repeat it. As A is one of the default operation, then subtraction will be done in a manner that B is subtracted from A. So if I have to create a representation for the same, so it will be A minus equals to B, that is A equals to A minus B. Then the value is stored in F000H. value stored in F000H. Okay, right? So likewise here, what I've done is I've translated the program into a program using 8085 instruction set. So likewise in the previous program, what we have is we have 06 being moved to A, 05 being moved to B, and we have subtracted the value of B from A, and we have stored the result in F000H, right? And then what we have is we have halt. Now likewise we have the operation code for MVIA is 3E, so 06 is data byte, okay? MVI opcode for MVIB is 06, data byte is 05. Now the opcode for subtract B is 90. For add it was 80, for subtract it is 90. So then again store the content of the accumulator. Opcode for STA is 32. Store the content of accumulator in F000H. So here, as I said, lower byte in lower address space and higher byte in higher address space, and eventually there is a halt, right? Okay, so as I've already said, whenever the microprocessor interprets the program, it always considers the first byte to be an instruction byte. So based on that, it will interpret all the other instructions that are participating in the program. Okay. Now again what I've done is I've stored the program in the computer's memory. So in C000, what we have is we have 3E, then 1 we have 06, at 2 we have 06, at 3 we have 05, at 4 we have 90, at 5 we have 32, at 6 we have 00, at 7 we have F0, and at 8 we have 76. Okay, right? So likewise what we have done is we have created a representation for the program in binary form as well. So this is the binary representation of the program that is capable of subtracting one number from another number. Now, you must be wondering that what if the value in case of addition exceeds 1 byte? Okay, right? Okay, so in situation, you see, in situation when the value when the value after summation, if it exceeds 1 byte, okay, that is the resulting value, if it exceeds 1 byte, then the carry flag will be set. Okay, right? So we'll come to the flag description of flags in case of 8085. So there are 5 flags. So we have a 0 flag, we have sign flag, we have carry flag, we have auxiliary carry flag, and we have parity flag. So we'll come to the description of each and every flag, but just remember, if the sum exceeds 1 byte in case of addition, then carry flag will be set, and in case of subtraction, if the value cannot be accommodated, then the borrow flag will be set. Okay, right? So in case of addition, carry flag will be set, and in case of subtraction, borrow flag will be set if the value cannot be accommodated. Okay, so please remember that. Now, let us move on to the third program, right, or third example. So what I need to do is I need to multiply two numbers, and I need to store the result in a address, specified address location. So here multiply two hexadecimal number using successive addition, because you know that multiplication is always implemented as successive addition, whereas division is implemented as successive subtraction. Okay, right? Again, I'll repeat it. In case of computation, multiplication is implemented as successive addition, whereas division is implemented as successive subtraction, right? So here, in order to multiply two numbers, what we need to do is we need to perform successive addition. Now here I prepared the concept note. So here just see A is initialized with 008 because A is the resulting location. A is the resulting register where the result is to be stored and eventually transferred to an address location. Now B is holding one of the operand and C is holding another operand. These are to be multiplied. So B is initialized with 05H and C is initialized with 03H. So what I need to do is I need to multiply B by C, right? Okay, that means I need to add, if I have to implement successive addition, I have to add B to A 3 number of times. Okay, right? So A plus 5 plus 5 plus 5. So if I add B 3 number of times to A, then it will be implementation of 3 5 into 3. So 5 is successively added 3 number of times, right? Okay, so here A is 0, B is 5, and C is 3. So you must have all come across a looping construct in C that's called as do while. So do A plus B, A equals to A plus B. So initially A is 0. So 0 plus B is 5. So 0 plus 5 is 5. Then we decrement the value of C by 1 because out of 3 times we have already added one time. So here C becomes 2. So while C is not equals to 0, what I'll do is I'll repeat the process. So it will add B to A 3 number of times. Okay, right? So eventually when C becomes 0, the loop terminates. And then what we'll do is we'll store the content of A to F000H. So here this particular looping construct will add B to A 3 number of times, okay, and then store the result of A to F000H. Now let us translate this particular concept node into an 8085 program. So now here what we have is we have MVI A comma 00H. So we are copying 00 to A, right? So that is we are moving 00 to A. Likewise, we are moving 05 to B. Likewise, we have moved 03 to C, right? Okay. So A is initialized with 00, B is initialized with 05, and C is initialized with 03, right? So now here what we have done is we have created a label, right? Created a label L1 where the control will be transferred until unless certain condition is not satisfied. Okay, so let us see. So here I've created L1. So this is simply a transfer control point. So L1, so whenever execution will be done, execution of instruction will be always done in sequence. Sequence, whether the label J label is just a tag provided with the address space. So now first these three instructions will be executed, okay, and then add B. So what it will do, it will add the content of B to A. So what is the content of A? Content of A is 0. So it will add 5 to A. So A will be 5. Now DCR is the instruction for decrementing the content. So the instruction is DCRC. So DCRC is the instruction that will decrement the value of the register by 1. Okay, right? So DCRC is the instruction that's capable of decrementing the value of the register by 1, right? Now JNZ, jump on no zero. So JNZ stands for jump on no zero. Where to jump? L1. Based on what condition? Based on the immediate condition that is there. So so jump on no zero. That means if the value of C is not 0, then you will transfer the control to label L1. So since here value in after the initial execution value of C will be 2, so which is not equals to 0, then the control transfer will take place to L1. Okay, again I'll repeat it. So these three instructions will be initially executed. Okay, then we have a label tagged with an address space. Okay, so add B. So first, since value of A is 0, 0, so add B. So it will be 0 plus 5. Then DCRC. So C will be decremented to 2 from 3. So since J and Z works with the immediate operation, so that is DCRC. So it will check for the value of C. So since C is not 0, it will move to label L1. So transfer control takes place to L1. Now again add B. So it's from the previous execution, value of A had become 5. So 5 plus 5 will be 10 now. Now again DCRC. So from 2, C will get decremented to 1. Again the value of C is not equals to 0, right? The control transfer takes place to label L1. Again add B. So from previous execution value of A was 10. So 10 plus 5 is 15. Now DCRC. So it will decrement the value of C from 1 to 0. So now this particular condition is not satisfied. So it will terminate the loop. So then it will come to this particular instruction, that is STA F000H. So now the value of A is 15. So 15 will be stored in F000H and then HLT. Okay, so this is the way how a looping construct works in case of 8085 programming. So just see, what you need to take care of is you need to take care of the decrement operation, and you need to take care of the transfer control instruction that you're using. Okay, so it works with the value of C, so that's why it creates a loop. Now likewise, what I have is I have opcode representation of the same program. So MVIA is 3E, so 00 is the content of A, right? So MVIB is 06, then 05, MVIC is 0E, then 03, then L1, okay, label L1, then 80 is the opcode for ADB, 0D is the opcode for DCRC, C2 is the opcode for J and Z. Now what we have is we have label L1. As I've already said, label L1 is a tag associated with a address space. So now this L1 is to be represented or replaced with the help of the address space. Okay. Now 32, then 00, F0, 76, right? Okay. So now let us see how this L1 is managed. So now at C000, what we have is we have 3E. At C001 we have 00. At C002 we have 06. Likewise at 3 we have 05. At 4 we have 0E. At C005 we have 03. At C006 we have 80. At C007 we have 0D. At C008 we have C2, right? That is the opcode for J and Z. Now this label L1 is to be replaced with the address space that is tagged with this particular location of the program. So just see 80 is tagged with C006. Okay, and since L1 is here, so what we need to do is we need to now replace this representation of label with the address space, because the control has to be transferred to this particular location. So at C009 we have 06, and at C00A, because after 9 comes A in hexadecimal, C00A we have C0. At C00A we have C0. So now C006 was the address associated with the label L1. Okay, so now at C009 we have 06, and at C00A we have C0, because we know that higher byte will go to higher address space, higher byte will go to higher address space, and lower byte will go to lower address space. So higher byte of the address will go to higher address space, and lower byte of the address will go to lower address space. So now the label is being replaced with the absolute address here, right? So every time whenever you fit in a label to a program, you need to always ensure that the label is replaced with the absolute address space. Then at C00B we have 32, right? C00C we have 00, C00D we have F0, C00E we have 76, right? Okay, so here after 9 we have A, because in the case of hexadecimal what we have is we have A, B, C, D, E and F, because it's a 16 base number. Okay, so this is the way how a program that has an iteration is to be required. Okay, so labels are to be created as and when required, and the labels are to be replaced with the absolute address whenever it is placed in the computer's memory. So I hope these three programs are well understood to you. Okay, so in the next class we will perform few of the operations and see how hexadecimal operation works. So thank you very much. We'll meet in the next class.